Assalamu alaikum dear students. Today our lecture is about chemical reactions. It is a continuation of the previous lectures, and actually we are still continuing the same topic, which is about the stoichiometry and chemical reactions and chemical equilibrium. Basically, we are trying to revise and understand the basic concepts of stoichiometry, and because most of the time in our environmental engineering, we will be while we will be dealing with the processes, we will be also taking care of the chemical reactions. So those chemical reactions must be in a proper balance, and the proper quantities of the material are required to obtain the required result, especially when we will be dealing with the optimization of the different chemicals which are used in our reactions. As you know, in different reactions and different processes, we are supposed to have different reactions, and all those reactions have some specific requirements, some specific characteristics which need to be fulfilled, like pH. We need to maintain pH, we need to maintain temperature. uh, in addition to this, we are also required to provide the optimum dosage of that chemical. And furthermore, when we are going to have a reaction, obviously there will be some reactants which will be giving us some product. Then those reactants again have some limitations. We call them as limiting reactants. It is just like uh, some reactant which is going to control the amount of final product. So if we have a specific amount of a reactant B, obviously it will have an impact on the overall production of the end products C and D. So we will try to find it out. Furthermore, we will be revising some of the basic stoichiometry concepts which you have already gone through, and you have revised it in the previous lectures. And again, we will have some practice on that. We will see how they are being implemented in our environmental processes, and what is actually their significance. So I think you have already gone through the basic concepts of mole and uh, percent composition of the compounds, and then the formulas of the compounds, and then empirical formulas, and then molecular formulas, and then writing of the equations in chemical equations in a balanced form. So all these things we will once again just have a brief and quick overview which will help us in our uh, process design at different stages. For example, sedimentation, for example, activated sludge processes, for example, our disinfection processes. So all these processes need a controlled environment and controlled chemical reactions, so that we can obtain the required products in the within the reaction. So then now if you see atomic masses, well, I think it's quite clear. I will just like to revise that carbon 12 is used as atomic mass reference. That is considered to be the most stable isotope, and the weight of that carbon 12 is considered to be as the unit, basic unit 12. And then we have some molar quantities, and I think it's again very well known. that Avogadro's number is equal to 6.022 into 10 power 23 is going to give us the amount of Avogadro's number which are present in 1 mole, and 1 mole is equal to maybe one atom, one molecule, one ion, one compound, or one uh, uh, radical. So 1 mole of carbon is equal to 12.01 grams. So one carbon atom is equal to 12 units, atomic mass units. So these are some basic terms. What is mole? So number of moles is actually what we are interested in. How many number of moles are present in a chemical reaction? So we will see its significance in our coming slides, which will emphasize why we are trying to focus on these things. Number of moles. What is the importance of number of moles? Well, so it's quite a repetition, like percent composition of a compound, composition of aluminium sulfate, uh, hydrous, which is alum, and hydrous aluminum sulfate is also there with H2O, 18H2O addition, but it's only aluminum sulfate. And how to find its molar mass? Simply multiplying it by the atomic weights, and then uh, when we have a total amount of the molar mass, then we can find the percentage of every compound separately. So every atom and molecule which is being used here can be separately found for its percentage, mass percentage. So aluminium sulfate, oxygen, these can be separated based on their percentage weightage. So then we have a molecular weight. What is molecular weight? It is the weight of one molecule of any compound. It's quite simple. When we talk about a molecule, it is actually it can be a combination of two atoms. So therefore it is maybe of the same atom, and then furthermore it can react with some other atom as well to form one compound molecule. So like H2O, and then like CO2, these are again molecular compounds. So the weight of one molecule of any compound is called molecular weight. And when you compare it with atomic weight is simply a single identity which is going to have its own atomic weight, unless and until that atom reacts with another atom to form a molecule, or it reacts with some other compound to get ionized. In that case, we will be having a molecular weight which is formed. Then how to represent this molecular weight? Normally we represent this molecular weight in terms of gram, g. Actually it is not a gram which is representing this weight, but we have generalized this term for chemistry, because we will be expressing our molecular weights and our moles and then our gram atoms and then equivalent weights all in terms of gram. Now this gram is not necessarily equal, will be giving us the weight which we are going to measure in kilograms. Or it's not like having 1000 grams of carbon will be giving us 1 kilogram of carbon. It will be not like that, but still it is just a representation. So just a standard to be as a representative of the quantity. So H2SO4, taking an example of H2SO4, So the molecular weight of H2SO4 will constitute of 2 atoms of hydrogen, and then 1 of sulfur, and 4 of oxygen. Now multiplying the respective amount of these atoms with their atomic weights will be giving us the overall molecular weight of H2SO4. So for example, we have 1 atomic weight of hydrogen, it will be multiplied by 2. Sulfur has 32 and it is only 1 atom, so it will remain the same. Then we have 16 atomic weight of oxygen multiplied by 4 will be giving us 64. So summing up all the atoms will be giving us 98 grams. So we have alum, which is a hydrated aluminium sulfate. So if you quantify this aluminium sulfate, you can find out that we will be getting 666 grams, 666 grams. If you further calculate it by yourself, aluminium has atomic weight of 27, and multiplying it by 2 plus sulfur multiplied by 3, and then we have oxygen, which will be multiplied by 12. 4 by 3, 12. We have 12 atoms of oxygen, and I think I missed H2O. It is 18 H2O, and H2O, one molecule is equal to 2 plus 16 is equal to 18. So 18 multiplied by 18 will be added up in this figure as well, and then we will be getting this 666 grams of hydrated aluminium sulfate. So this is how we can find out the different molecular weights. Similarly, we can find the calcium carbonate and the molecular weight of calcium carbonate. Again, calcium has 40, carbon has 12, and then oxygen has 16. So multiplying 16 by 13, 3 plus 12 of carbon plus 40 of calcium will give us 100 grams of calcium carbonate. So molecular weight is the sum of all the atomic weights of all the atoms in a molecule. So this is the simplified form of the definition of molecular weight. Now we move forward to number of moles. What is number of moles? You know mole, what is mole? It is a unit to represent something, and in 1 mole we are going to have how many actual numbers of maybe atoms, of molecules, or ions, or radicals, whatsoever it is. And how many will be those? It will be 6.03 into 10 power 23. So now we will be quantifying how many number of moles are there. So simple formula for finding out the number of moles of a particular compound is given by the given weight, in which we are going to determine, divided by molecular weight of that compound. So given weight will be known to us, that how much weight we are using of any compound. For example, NaCl, for example, calcium carbonate, for example, H2SO4, whatsoever it is. So it will be represented as given weight divided by the molecular weight. So if we have 350 grams of calcium carbonate, if we have 350 grams of calcium carbonate, how many number of moles will be present in this compound of calcium carbonate? How we can find it? So 350 will be divided by the molecular weight of calcium carbonate, and that is 100. It is 100 because calcium is 40, carbon is 12, oxygen has 3 atoms, so it will be having the share of 48. So 48 plus 12 plus 40 will be giving us 100. So overall the number of moles will be 3.5 for calcium carbonate. Similarly, please go through the second example, which is having millimoles, which will be dealing with milligrams. So this milligram is will be giving us millimole, and then 1 millimole is represented in the form of 10 to power 3 moles. Ten to power minus 3 millimoles, sorry. So again we have the molecular weight of H2SO4, and we will be 196 multiplied by 10 to power minus 3 divided by 2 plus 32 plus 64 is giving us 98. So it will be divided by 98. So 196 multiplied by 10 to power minus 3 divided by 98, and it will give us the number of moles in 196 milligrams of H2SO4. So this is something about the number of moles. Moving forward, there is another term which is called equivalent weight. So earlier we studied molecular weight, now then number of moles, and now equivalent weight, another very important term because we normally use it in our analytical testing of water quality, and particularly when we are dealing with hardness and when we are dealing with the alkalinity, and then we need to express the results in equivalents in the form of equivalent weight. So that's why it is important for us to understand this term that is called equivalent weight. What is equivalent weight? So when we try to understand how much potential this compound has to react with some other compound, we need to express it in terms of valency. So the molecular weight divided by the valency is going to give us the equivalent weight of that compound, that molecule, or that atom. So similarly, if you find out the equivalent weight of calcium carbonate, you can see that calcium carbonate can be dissociated into calcium 2 plus ions and CO3 2 minus ions. So the number of electrons transfer which has taken place or possibly to take place between two compounds, between two ions, between two atoms, between two molecules is radicals is expressed as our equivalent weight. And then these are the compounds which are not ionized. So NaCl is another example. So Na, it will dissociate into Na plus and Cl minus. So if you check the valence number of these ions and radicals, you will observe that calcium carbonate is going to have a valence number of 2, and similarly NaCl is going to have a valence number of 1. So if you are going to find the equivalent weight of calcium carbonate, how you will do it? You will first of all find the molecular weight, which is 100, then divide it by 2, which is the valence number of calcium carbonate. This is the simple form in which we will be doing it. We will be finding the equivalent weights, and then in the case if we have ionized uh, ionized radicals and ionized atoms. Here is example magnesium 2 plus ions. So 2 electrons have already been given. If you check Mg2 plus, what it actually means, that it has two electrons in its outer shell, which has been already given. So if you see the above example NaCl, in Na we have 11 electrons, so 2 in the innermost, 8 in the middle second circle, and 1 in the extreme circle. So it has the potential to donate 1 electron. It can lose 1 electron, and when it loses 1 electron, it will be getting the charge Na plus, because overall now the charge has become positive on the sodium atom. Next to it we have chlorine, which is going to have 17, and if you check the configuration, 2 electrons will be in the innermost, then 8 in the second circle, and then 7 in the outermost circle. So now it has the capacity to get 1 electron so that it becomes stable. So sodium has 1 electron extra in the outermost to lose, and chlorine has 1 electron space to receive. So that electron will be fitted in, and it will complete the whole compound NaCl. After this dissociation, after this ionization, now the sodium has already lost 1 electron with having overall positive charge, and chlorine has already accepted 1 electron. Now its charge has become negative overall. So this is the distribution. Similarly, in the next case, if you see here, we have magnesium 2 plus, and it has the capacity to lose 2 electrons, because the atomic number of magnesium is 12. In the innermost it is going to have 2, in the second circle it is going to have 8, and in the outermost circle it is going to have 2. Now it has the capacity to lose 2 electrons. So once it gets ionized, it means it has already donated 2 electrons to some other radical. So in this case, you can observe that this Mg2 plus will be getting ionized. So if you find the equivalent weight, then we will be simply dividing the atomic weight by its valence number, and it will be giving us 12 gram. Now we have another term that is called gram equivalent. This term is again associated with the equivalent weight. So it is the similar form of number of moles, as we defined number of moles equal to given weight divided by the molecular weight. Similarly, we will be finding out the gram equivalents. Now the number of moles like the number of moles which are associated with molecular weight, we have a gram equivalent which is associated with the equivalent weight. Now simply modify the formula accordingly, and we will get gram equivalent is equal to gram weight in gram over equivalent weight of that compound or molecule. This will be giving us gram equivalent. And how we will be finding out? We need given weight of any compound, and we also need the equivalent weight. So we have the example, find gram equivalent in 350 grams of calcium carbonate. So what is the given weight? That is 350. And what is the equivalent weight of calcium carbonate? The equivalent weight of calcium carbonate is 50. Now may I ask, what is equivalent weight? Equivalent weight is molecular weight divided by the valence number. Now molecular weight of calcium carbonate is 100 and its valence number is 2. When we will divide it, we will get 50. Now this 50 is the equivalent weight of calcium carbonate. Now fitting it in this equation, you will find 350 divided by 50. Now this 50 is the equivalent weight. It will give us 7 gram equivalent. So as equivalent weight associates with one electron transfer, number of gram equivalents in chemistry signifies how many number of electrons transfer can possibly take place or have already taken place. Now I will require you to have some consideration how to differentiate both of them. So in equivalent weight case, we only discussed one time transfer of electrons, one electron moving from sodium and joining the chlorine outer orbit. So what was it going to give us? It was one time electron transfer. Next to it, we have now found out the gram equivalent. Now we have 7 gram equivalents. Now this gram equivalent means how many times there is a possibility of that transfer. So it will be having 7 times transfer possibility. So 50 gram is associated with 1 electron transfer and 350 gram is associated with 7 electron transfers. Now please have a look at it. It is the gram equivalent principle. It means that 1 gram equivalent of any compound reacts with 1 gram equivalent of another compound and produces 1 gram equivalent each of the respective product in a reaction. So it's quite simple. Example is A plus B plus C is going to give us D plus E. A, B, C are the reactants. D and E are the products. Now each is going to have gram equivalent. Let's say 3. Now if A is having 3 gram equivalents, it will react with 3 gram equivalents of B, 3 gram equivalents of C in order to produce 3 gram equivalents of D and 3 gram equivalents of E. So if this is the case, we are going to have a similar production of the end product. Same amount of gram equivalents will be produced. Now let's prove it. We have an example of H2SO4, and it is going to be dissociated into 2H and sulfate ion. And what is the molecular weight of these compounds? Let's write it here. So 98 grams of H2SO4, and then 2 grams of hydrogen and 96 grams of sulfate. Now let's find out the given weight. For example, given weight of H2SO4 is 600 grams. This is known to us. H2SO4 given weight is 600 grams. So from this 600 grams, how many grams of hydrogen are produced, and how many grams of sulfate ion are being produced? We need to differentiate between both. So from this 600 grams of H2SO4 given weight, please calculate the given weight of H and hydrogen and sulfate ions. So how we can do it? Using the unity formula. Simply find it out here by 600 divided by 98 and multiplying it by the molecular weight of H2SO4, we will get 600. Multiplying by 2, we will get 12.24 grams, and multiplying by 96, we will get 587.6 grams. This is the given weights we have calculated. From these given weights, we will be calculating the gram equivalents, because we are going to prove that gram equivalents must be same for every compound, either on reactant side or on the product side. So let's check whether gram equivalents are equal or not. Let's find out the gram equivalent for every compound. So starting with the H2SO4, so how we can find the gram equivalent? We need the given weight divided by the equivalent weight. So given weight for H2SO4 is 600, it is known to us, and 49 is the equivalent weight of H2SO4. What we are getting? 12.24 grams of H2SO4. This is gram equivalent. Please remember, gram equivalent. Now finding out the gram equivalent for hydrogen, we have 12.24 given weight divided by the equivalent weight 1, which is giving us 12.24 gram equivalent. Then we have sulfate ion. What is the given weight for it? We have already calculated. It is 587.6. So divide it by the equivalent weight of sulfate ion, we will get 12.24 grams of sulfate ions. Now if you see here, all the gram equivalents of these compounds are same in the equation. So whether on the reactant side or on the product side, we are going to have same gram equivalent. So once you know a gram equivalent of any compound, or you can find the other unknowns as well. So it is easy to reverse calculate the given weight of any other compound, or if you know the given weight of the B compound, you can find what compound it is. So we can have this kind of calculations if required. So This is according to the gram equivalent principle, and the gram weights have been calculated, which are equal, and they are reacting on equal proportionate basis. So this was something about the gram weight, gram equivalent. Now we will be talking about the normality. What is normality? It is the strength of the solution. So no solution is used in its pure form. No chemical is used in pure form, purest form. We need to dilute it according to our requirement. If we are using H2SO4, if we are using HCl, we need to have its specific normality, which is required for that particular usage or particular reaction. So how we can do it? So what is a solute? It is the amount which is being added up in a solvent, which is going to be dissolved in a solvent. So solvent is something in which it is the solute is being dissolved. So solute is minor part, and solvent is the major part, because the solute is supposed to be dissolved in the solvent. Then a combination of both solvent and solute will be giving us solution. So this is called a solution when we will be having a mixture of solute added up in solvent and properly mixed. A chemical can never be used in pure form. It is diluted, and then a mixture is called solution. Now normality is defined again in terms of gram equivalent of the solute. So number of gram equivalents of solute divided by volume of solution. So we have already learned how to find the gram equivalents. It is the given weight divided by the equivalent weight. So you can revise it by yourself. Then this number of gram equivalent of solute will be divided by the volume of the solution, and then it will give us the normality. So we have an example like 0.02 normality is less than 0.08 normality, which is a stronger solution, because the volume will be the same, only the solute is supposed to be changing. So if we are going to have higher value on the upper side, as a numerator, then we will be having a comparison, and in this way, especially when our volumes or volume of solution are same, only the solute is changing. So if we have a higher concentration, higher gram equivalent of a solute, it means it is going to have a higher strength, stronger compound will be formed. So keeping X, that is the solute gram equivalent of solute, constant, and V1 less than V2, N1 would be greater than N2. Again, it is our saturation process, and it can be found in terms of concentration, because the solute divided by the volume makes the dilution factor. So if the volume is higher, is more, it means the dilution is more, and when the dilution is more, it will be giving us lesser normality, lesser strength. Normality principle, we have a normality principle. According to it, N1 V1 is equal to N2 V2 if the solute is constant. We have another term that is called molarity, and it is also indicating the strength of the solution, but it is associated with number of moles. So earlier we were talking about gram equivalents. Now we are talking about number of moles of solute. So earlier we divided gram equivalent by the volume of solution in liters. Now number of moles of solute divided by the volume of solution in liters. So there is a relationship between normality and molarity. Sorry, it is molarity. I have mistaken. So the number of gram equivalent divided by volume of solution in liters, it is going to give us, this is the normality formula, and if you find what is gram equivalent, it is given weight by equivalent weight. It can be incorporated here. And then what is equivalent weight? So equivalent weight is equal to molecular weight divided by the valency. So fixing it in the equation, we can simplify it like this, and then given weight over molecular weight is also giving us the number of moles, and then this number of moles divided by the volume of solution in liters is giving us molarity. So this molarity is incorporated in the equation, and when molarity multiplied by valency will be giving us normality. So this is the relationship between the normality and molarity. It is actually molarity. Sorry, some spelling mistake is here. Then we have empirical formula and a chemical formula that represents a simple whole number ratio of the number of moles of element in a compound. Then the molecular formula shows the actual number of atoms which are being used. And then here we have empirical formula 1. So from composition we can find the percentage, and then we can find the ratio proportion of each percentage, and then that percentage will be defining the subscript of that atom. So I think this can be done simply by getting the simple ratio, and then mole ratio is here. We have empirical formula 2. That this is another example, so please go through this example as well. Another example. So these are quite simple examples, you can find it by yourself. Balancing of the chemical equations. So I think it's already well known to you. You can do it by yourself. This is the revision of stoichiometry equation, chemical reactions. So this is the application of our stoichiometry studies. So if you see this figure, I think it's well known to you. We need to have an equilibrium. So whenever we have a balanced reversible reaction, then we have an ionization constant. That ionization constant is normally represented by K, and Further, that ionization constant is going to sustain the equilibrium between the reactants and the products. So normally we have a balanced reaction when water dissociates into hydrogen and oxygen ions. It readily reacts, and reversible reaction initiates, and it reverses back to water, and then again it dissociates. So this chemical balance is existing in our system. Now based on this we have developed our pH, because when a hydrogen ion concentration is increased, that means we are adding up the ionic values, and every ionization constant of K is going to have number of moles in as 1 into 10 to power minus 7 moles of hydrogen, and similarly equal amount of hydroxyl ions are present in a dissociated solution. So whenever we add some acid in that solution, H plus will be added up, and that H plus will directly influence the concentration, and it will lower the molar ratio, and then 10 to power minus 7 will be reduced. So overall we have a figure of 10 to power minus 14 as a multiple of the two molar concentrations of hydroxyl ion and hydrogen ion, and then we will be taking the negative log. We will take the log on both sides to represent the molar concentration, and it will be defining the amount of H ions and then hydroxyl ions in terms of ratio starting from 1 to 14. So based on that we will be describing our acid and base of a reaction, and similar reaction exists when we are going to dissociate calcium carbonate. So if you remember the phenolphthalein experiment you have done, you are adding up the hydrogen H2SO4 from the burette to the flask, and you are adding up the H plus concentration. Hydrogen ion concentration is being added up in the flask. So this adding up is actually going to give us more values, and then it will be reducing the hydroxyl ion concentration and increasing the H ion concentration, and thus increasing the acidity. So same is the expression here. These are the compounds which are different species of the CO3 dissociation, and you can observe that here on one side we have the molar concentrations, and initially at lower pH we will be having CO2 and HCO3 minus ions, and which are gradually changing with the pH, and we are going to have a completely different species. By the end we are going to have different pH level maintained. This is just one example how the equilibrium of the chemical reactions is important in our environmental engineering and different processes. So two examples we considered. First of all is the dissociation of water, H2O, which dissociates into H2 and then hydroxyl ion, and similarly we have another dissociation, that is the calcium carbonate dissociation. And when we study this hardness and alkalinity, we normally express these species which are CO3, carbonate ions, bicarbonate ions, calcium ions, magnesium ions. We express these species in terms of their molar concentrations and their pH levels. And for its control we have an phenolphthalein test as well, methyl orange test as well, with the help of which we can determine at what level the carbonate ions are going to convert into bicarbonates, and then again by adding up we will get the reverse reaction. This is another example of the application of the chemical equilibrium. Normally, CO2 is available in our environment in excess, and it is required by the plant species and algal growth, and so it is a very important uh, uh, process with the help of which CO2 is kept balanced in our system, and algal growth is going to play an important role in balancing these CO2 levels in our atmosphere. Similarly, you can go through it in detail, and then we have some more additions and then dissociations. Here we have again the same reaction, we talked about it earlier. So the chemical reaction is a process that leads to the transformation of one set of chemical substance to another, reactants and products. And then chemical equilibrium, we talked about it as well, and some of the parameters, and this is the application. So that's all for this lecture. Thank you very much.